Hello and welcome back to Fluid 2000. This is lesson 4, part 2. We're going to talk about directional control valves and flow or speed control. Now, as mentioned in the previous presentation, valves provide a variety of fluid control options. We looked at pressure in the last presentation and what things you can do with pressure. I can set my maximum pressure. I can reduce pressure to a certain part of the circuit. I can have parts of the circuit, actuators, move in sequence, one, then the other, then a third. I can also use it to balance and all kinds of other things using pressure as the controlling medium. Now we're going to see what you can do by changing the direction of the fluid and what that can do for you. So directional control valves are pretty common devices. And here you have 3 of the most common types. On the left, you have the rotary spool, which is manually operated and moves by having a cam move inside of the case, opening and closing off ports that allow fluid to flow through. A sliding spool valve is by far the most popular because of its compact design, and it can be controlled a number of ways. Most of them are just using, quite literally, a sliding spool that's controlled by either mechanically, by the operator, or electromagnetically. Really can be used by fluid pressure as well in an automatic system, but simply it's just the sliding spool. And it all comes down to the O-rings and passages through the case and what's blocked off and what's exposed depending on the position that the valve is in. Okay, let's start with a simple on-off valve. This particular one is very common. In the trade, we call these red hats because usually the solenoid end has a red cap on it. And it's just a simple plunger that's surrounded by an electromagnet that, when power is applied to the magnet, attracts that plunger up into it. Now, depending on how the valve case is constructed, it's either a normally closed valve or a normally open valve. And it's very hard to tell by just looking at it. You really have to look at the schematic diagram on the valve or cross-reference it to a part number. Otherwise, your system will do the exact opposite of what you want it to do, even though the part looks exactly the same. Now, in this particular one, you have a return spring which returns it to the position that the spring is on, and that's always your big clue here. So in this top example, it's a two-way solenoid valve and it's normally closed. Both the inlet and the outlet are isolated from each other unless the solenoid coil is engaged, at which point the valve switches and fluid is allowed to flow through the inlet to the outlet. The bottom schematic indicates the exact opposite. The spring return returns the valve to its open state where fluid will flow through it unless the solenoid is energized, at which case the fluid flow stops. Here's an either-or valve, they call them, and this one is manually operated. So as pressure is applied to the inlet, it is either given over to outlet 1 or outlet 2, depending on which position you have it in. So in this particular case, it's either on or off, either way. Now, limit switches are a way of controlling the extension of a cylinder, is where you see them most often. When a cylinder gets to the end of its extension or the end of its retraction, a lot of times it will trip a roller cam limit switch, or sometimes you'll have little reed switches or magnetic proximity switches that sense the actual piston end going over them. But either way, they're designed to tell you the position of the actuator. And this can be fed back electrically, usually, back to the control system to allow it to change position or to go on to its next step in the process. So directional control valves, as mentioned, can be either mechanically or electrically, hydraulically, or with some kind of a pilot fluid. In this particular example here, we have a pneumatic three-way valve, spring return, and it's a closed center. I know it's closed center because all four of the ports, A, B, P, and T, in its center position are isolated from each other. And it's a pilot operated device because I can see the two end caps have an arrow that points in, indicating that pilot fluid will come in. And since these are not shaded in, that indicates to me that it is a pneumatic valve. Now, directional control valves have a lot of the magic inside of them is in the construction of the case and how the passageways are laid out. And that's why another reason why it's extremely important that you have a clean hydraulic system. The clearances between the rubber seal of the spool and the spool body itself are very small. And it doesn't take much dirt or contamination to get in there to either damage those O-ring seals or carve a channel in the actual case of the valve itself, allowing it to leak by. Fluid cleanliness, of course, we covered before, is extremely important. And in a lot of these valves, particularly pilot-operated valves, there are a lot of extremely small passages that have to be kept clean. If they're not kept clean, the mechanisms won't work and the system will fail. Okay, springs affect the function. On the diagram on the left, you have a spring on either end of the spool valve. This centers it in the off position in the middle. This particular valve is a closed center valve, meaning that none of the four ports are vented anywhere else and they're dead-ended when not in use. This is a pilot valve because you see the little arrow indicating pilot fluid coming into the device, and it's a hydraulic valve because the pilot fluid is shaded in. Spring return, so it's either one position, the other position, or nothing happens in the center with this one. Okay, so if it's actuated in one way with fluid pushing from the left, P goes through to A, B goes back to tank. If it's actuated from the right-hand side, pushing left, you'll see that P will go to B and A will bleed back to tank. And of course, if I don't have anything triggered, it will return to the center position. On the one on the right is only a 4-port 2 position. Still has the same 4 ports. However, its default position is going to be the one on the side of the spring. And you'll see that P would pump to P would pump to B and A would go back to tank. When I energize it using a pilot fluid again, you'll see that P will come through to A and B will go back to tank. So this could be used as an automatic flow control depending on a pilot pressure or something along those lines. Okay, spring symbols will indicate how the valve will react. The valve schematic on top shows springs at either end, so that means it's going to be self-centering. And the symbol for hydraulic actuation, and I know that because of the pilot line and the fact that the arrows are shaded in. Once the hydraulic actuation signal disappears, the valve will go back to center. So here you see that the channels that are actually cut into the valve body are what actually determine where the fluid goes. All the spool does is move in and out, back and forth on both of those springs, depending on which way the pilot fluid determines that the spool should be pushed. Very simple design, but very robust. And you get a lot of actuations in one of these devices in a long lifespan. So the schematic drawing for the center position is very important and indicates the type of valve you might require for your process. Again, these valves coming in the box, coming out of the box, put them down side by each, will look identical. It's very important that you read the literature that comes with the valve and the schematic that's stamped on the valve body or attached with a tag. Okay, so on the closed center is very useful if I want to position an actuator like a cylinder in a set position incrementally. For instance, let's say that I have a bucket excavator and I'm digging a hole and I have a lever actuator so I can go back and forth, and the center position means it just stops. So I can dig with my bucket and just hold it there by releasing it and then moving it and then releasing it the other way. So it will hold its position. The open center, however, bleeds everything together when not in use. So it equalizes the pressure throughout the system when not in use. Tandem center dumps back to the tank, and it will hold the actuators in their position because they're dead-ended, just like the closed center, but it allows the fluid to flow through. And that can be useful in cold weather applications where you can have an issue with actuators freezing up. I can use in one of the tandem centers, and that will allow warm fluid to go through the valve body and keep it warm and keep it moving. The float center is very good for regenerative circuits. Regenerative circuits are excellent when I don't want to when I want to use the returning fluid from the system to help me move another actuator in another direction. So I can use that energy to help regenerate back into the circuit so I don't have to take that energy from the pump. So depending on the application for your hydraulic system, it's very important that you get the center position right on your spool valves, even though they look the same. So here we have an example of a spool valve, and it doesn't have a spring return on it. So I can use this and push it in one direction, keep it in that direction, pull it back to the center to stop it. So it doesn't have a spring return. I have to physically return it to the center position. But other than that, it's a closed center device. And when it's activated towards the left-hand side of the page, you will have P pumping into A, B back to tank. And if I were to flip it the other way, P goes to B and A goes back to tank, right? So very simple operations. And most of your spool valves are going to be 4-port, 3-way spring return devices. That's the most popular out there. The only difference is going to be in that center and whether or not it's a tandem, a closed center, or a regenerative circuit. So a basic check valve. This is a basic check valve for a low flow application. So this would be in metering or pilot lines or something along those lines. It's a ball sitting on a seat and a spring that pushes that ball up against the seat. Now, if fluid tries to flow from right to left, it can't do that because the spring has that ball held up against the seat, and any extra pressure against that ball will just seat it better across that seat. Now, if I overpressurize it, of course, I can get some leakage by there and then out and out valve failure if I'm not careful. In the free flow position, this spring, even though it's very similar in construction and design to the pressure relief valve, the direct acting pressure relief valve, the spring pressure is nowhere near it and it's not adjustable. So this spring is designed to just hold that ball up against the seat. Nothing more, nothing less. You don't want to have any more pressure than necessary to allow that fluid to flow, because you're going to have a loss over here. And I don't want to have any of those parasitic pressure losses in my system. Just enough to get it going, right? Basically it. So a Poppet Checket valve would be more for line side or higher pressure applications. This Poppet rides in the entire interior diameter of the valve body, so it's very centered. It doesn't wiggle around or move. The spring is on the inside of the Poppet, which keeps all of the force directly on the Poppet wedge here, which is usually some kind of a graphite or brass, which provides a good seal. But again, this spring, even though it has a little bit more spring compression than the ball valve, still doesn't take much to open it up. And because of the conical shape, you have that reduced surface area upon cracking, which allows the fluid to flow through much easier through this type of a check valve. Okay. The last type of valve is the flow control valve or speed control valve. And here it's in the meter in line. In other words, it's in the pump line. So this will have an effect on the speed of everything that comes after it in the circuit. Now you'll notice by the A and the B pressure gauges here that there is a little bit of pressure loss across the flow valve. It's kind of a cost of doing business. The valve is designed to minimize that. However, because you're taking a nice laminar flow through the conductors and making it go through a passage and change directions, you're introducing some turbulence into the flow. As a result of that, you can get a little bit of a pressure drop on that. And if you have air and stuff in the system, these can be noisy too. This is where you'll hear it. Okay, this is pumping against a closed center, and as a result of that, the pressure would probably build enough that it would start to bleed off through my PRV valve to control the pressure ultimately in the system. So by placing that meter valve in here, I really don't need these two valves. This valve here is similar to this one. The only difference you'll notice is this one has a check valve on it. The reason that the check valve is there is it allows the fluid to flow back in this direction, back to the tank when it's unloading, but it will control the speed of it going this way. So this flow control element will control the speed of the actuator going out. This will control the speed of the actuator going back, right? So when I go this way, when this is pumping this way, again, fluid will go through here. It won't go through the check valve on the bottom side because, well, it's pumping up against that closed ball. It must go through the restriction and it will retract at a slower speed. Now, I could replace both of these valves with one valve on the inlet. However, both of these would go at the same speed, both in the extension and the retraction. By using two as opposed to one, even though I will incur two pressure losses, even though they be small, I can have this device extend at a different rate than it retracts. So I can have it, let's say, extend at 3/4 speed and retract at half speed. Whereas if I have it in the pressure line, I can't do that because all of the flow is metered from the point downstream of that restriction. So there's your basic differences. Now, in a meter out design like this, and it's showing the check valve from the inlet to the outlet, I am allowing fluid when it's pushed to when it's pushed to one position for the fluid to flow to retract the cylinder back in, retract the rod back into the cylinder very easily because it pushes it off of that seat. But however, when I go to charge the system up, I can control the speed of the extension of that cylinder by changing the setting on this flow controller here, by changing the side of the orifice here. Now, this can be useful with gravity loads, but you have to be careful with this one. Fluid leaving the cylinder is not controlled by the pressure relief valve. So you can have an issue where you can overpressurize this system by having this shut down too much and creating too much of a load on the system for it to move it out of the way. So this is a meter outflow. And again, I can install this one line in here to replace the two on the cylinder side. Again, they will do the same thing as the meter in. The only difference being that on the meter out, you can have an issue with, again, pressure. And the meter out is plumbed in the return line. Note the flow control is in series with the main return line. So this will act as a flow control, but really, if I'm going to use a flow control, I would much rather have it on the inlet line if I'm just using it for one, or I would have two separate flow controls if I needed two speeds on either the extension or the retraction of the cylinder. So a very simple device of flow control. Most of them have check valves inside them, so it will only restrict the flow in one direction. If it doesn't have a check valve, it will restrict the flow in both directions. Okay, here's an example of a bleed-off. Bleed-off valves are a little different because they're wired in parallel with everything else. Like before, when we had the meter-in valve in series, the fluid only had one choice, and that was to go through the flow controller. Here, it doesn't need to go through the flow controller. And of course, fluid will take the path of least resistance. So I can have this system set up so that it will run back to the tank to keep my fluid running through my filter section, let's say, while still having the ability here to have my my closed center control, so my inching. And here we have it, interestingly enough, going back to tank through two flow restrictions in parallel. And they bleed off to the tank all independently, which is totally different than any type of flow control. The bleed off valve is plumbed into the pressure line, which increases efficiency by dumping excess fluid before it gets a chance to get pressurized. So the pump can circulate the fluid, and the motor doesn't have to work as hard because it's not pumping against any head pressure. So this is a great way to save energy on a system. Now, if I added an accumulator to this system, I could actually reduce even further the amount of energy required to run my pump. Okay, so this is just a quick introduction to directional control valves and also to flow control valves. And in the coming weeks, when we get into the lab and I do the demos in the lab, you'll see how these devices are used with each other to create a complete automatic system. Well, thanks for tuning in, and we will see you again next time on Fluid 2000, where we will continue with some of the ancillary components, such as accumulators and things along those lines. So thanks a lot, and we'll talk to you later.